In this section, we will use Euler's formula to find an nth root of a complex number. All right, now let's try an example. In this example, we are being asked to find the nth root of a complex number. Now, nth root, because sometimes it might be the square root, sometimes it might be the third root, or the fourth root. In this example, we're being asked to find both square roots of z equals 1 plus the square root of 3 times I. Now, what do we mean by both square roots? Well, so let me just give you some examples from the real number world, and then I'll show you how that applies to the complex number world. If you are given, say, something like x to the second equals 4, to find the square root, you're going to square root both sides. Now, when you do that, you get not only plus, but you also get minus the square root of 4. So a square root has two possible roots. If this were a cubed root, it would possibly have 3 cube roots. All right, so that's what we mean by that. Now, if I'm just being asked to find the square root of 4, and that symbol is being used, the square root symbol, then what that means is you're being asked to find the primary or the principal root. And that symbol actually means that we're just looking for positive 2. Now, I'm going to show you how all that relates to the complex numbers. In this example, we are being asked to find both square roots, so we are going to be looking for 2 answers here. All right, so let me just erase that. Didn't mean to cross it out, but let me erase it so that we can deal with just our complex numbers, okay? So, step 1. Step 1 is to write the complex number in polar form using Euler's formula. All right, so Euler's formula. So we have been given an x and we have been given a y, and here's what we know. We know that x is equal to 1, y is equal to the square root of 3. So if we plotted it, we would be in quadrant 1, wouldn't we? So that's important to know when we go to find theta. All right, so I'm going to have x to the second plus y to the second equals r to the second. And so 1 to the second plus the square root of 3 to the second is r to the second. So that's going to be 1 plus 3, which is 4. And I'm going to say I have a radius of 2. Now, of course, I could have a radius of plus or minus 2, but Euler's formula uses positive radiuses. So we're just going to say 2. All right, now let's figure out what theta is. So we can either use tangent of theta equals y over x. Okay, my y value is the square root of 3. My x value is 1. If you know what angle produces a tangent of square root of 3, then go for it. If you don't have that memorized, then maybe you want to use sine, which is y over r. My y value is the square root of 3. My r value is 2. If I feel pretty confident with that r value of 2, I might use the sine instead, because I do have memorized what angle produces a sine of the square root of 3 over 2. Or maybe I want to use cosine. Cosine is x over r. My x value is 1. My r value is 2. No matter which one of these you use, you'll get the same theta. All right, so you decide what works best for you. Whichever way you go, you should be getting a theta equal to, let's see, I'm going to use cosine. What angle produces a cosine of 1/2? I believe that's going to be pi over 3. Now, here is where finding both square roots comes into play. Using the theta of pi over 3 gets me one of those roots. Using a coterminal angle to pi over 3 is going to get me the other root. So what is a coterminal angle to pi over 3? Well, I can either add 2 pi or I can take away 2 pi. 2 pi in thirds is 6 pi over 3. I'm going to take away 6 pi over 3, and that's going to get me a theta value of negative 5 pi over 3. All right, so those 2 angle measures are going to get me my 2 different roots. Now, if you're ever being asked to find just the principal root or the root, just one root, not both, but just one, then in complex numbers, the principal square root would be found by simply using the angle that is between the interval of -pi to pi, including pi. So if I were being asked to find just the square root or a square root or a principal square root, then I would only be looking at pi over 3. And in fact, that's the answer that your calculator would give you if you tried to take roots of a complex number using your calculator. I'm not going to show you that, but it is something that you can do, and if you want to know more about that, you can certainly ask me. Okay, so let's use both of those angles. I'm going to say that z, the square root of z, which I'm going to write as z to the 1/2 power. So we're going to take the nth root by raising it to the 1 over n power. I hope that you recall from past classes that if you have something like the square root of 4 with that symbol, that's the same thing as 4 to the 1 over 2 power, the 4 being raised to the first power and the index being 2. That's something that you should have learned in a previous class. So if you were being asked to say the cubed root, then that would be z to the 1/3 power. All right? So z to the 1/2 power, if I take the root on the left, then I would need to take the root on the right. So I'm going to raise that to the 1/2 power. Now, why was I told in step 1 that I should rewrite this using Euler's formula? Well, that's because Euler's formula allows you to write that sum as a product, right? So Euler's formula would turn the complex number of z into 2 times e to the I, what was my theta? Pi over 3 power. That was one of my options, right? So that's going to be raised to the 1/2 power. Now, here's what you may or may not remember about raising things to powers. If you have, let's say, a plus b, and you try to raise that to the 1/2 power, that does not equal a to the 1/2 plus b to the 1/2. However, if you have a times b to the 1/2 power, and that will equal a to the 1/2 power times b to the 1/2 power. So you can distribute the exponent in multiplication. You can't with addition. One more thing that you can do, let's just point this out. If you had, let's say, a to the 4th times b to the 1/2 power, then when you do that distribution, you're actually multiplying those exponents. So that would become a raised to the 4 times 1/2 power. And then, of course, b, this is a 1 right here, so that would be 1 times 1/2 power. Now, all that's going to be important here in just a minute, but I'm going to erase all this for now because those are skills that you probably, hopefully know and just needed a refresher. Okay, so my z to the 1/2 power is equal to 2 times e raised to the I times pi over 3 power, or it's going to equal 2 times e raised to the I times -5 pi over 3 power. I'm going to put both of those in there. And now I can distribute that 1/2 through, so I'm going to have 2 to the 1/2 power times e. Let's see, what is 1/2 times pi over 3? That's going to be pi over 6i. Or I'm going to have 2 to the 1/2 power, e to the, and when I multiply this one through, I get -5 pi over 3 times 1/2 is -5 pi over 6i. Now, technically, I'm done. I just found the square roots of this complex number. However, if you start with something in rectangular form, you should end it in rectangular form. So my last step here, well, maybe not my last step, but I'm getting close. My next step is to take these two answers that I have and put them back into rectangular form. All right, now I'm going to do one thing first. I'm going to rewrite 2 to the 1/2 power as the square root of 2, right? That is what it equals. And, you know, multiplication is commutative. That's why I was able to write either I times pi over 6 or pi over 6 times I. The order doesn't matter. Sort of liked the I better on the end there. So I'm going to have square root of 2. When I say equals, this is z to the 1/2 that equals. And so e to the negative 5 pi over 6i. All right, so I'm going to take this back into rectangular form. This is going to be the square root of 2 times the cosine of pi over 6 plus I times the sine of pi over 6. And that equals, I'm just going to distribute and distribute. So I'm going to have square root of 2. The cosine of pi over 6 is the square root of 3 over 2 plus I times the square root of 2 times the sine of pi over 6, which is 1/2. When I multiply that out, remember this square root of 2 is over 1, so that's going to be square root of 6 over 2 plus the square root of 2 over 2i. All right, and that is a good final answer. You might sometimes see that final answer written as, since we have a common denominator, right, square root of 6 plus square root of 2i over 2. You could write it like that as well. It just depends on maybe what the instructions are, but I'm perfectly happy with the way that it is. And then I need to do the same thing for my other root. So square root of 2 times the cosine of negative 5 pi over 6 plus I times the sine of negative 5 pi over 6. I'm running out of space. And that calculation is, what is the cosine of negative 5 pi over 6? Well, cosine is an even function, isn't it? So that means that negative 5 pi over 6 is the same as the positive 5 pi over 6. Cosine of 5 pi over 6 is, what is that, negative? Let's see, 5 pi over 6. Cosine of 5 pi over 6 is negative square root of 3 over 2 times negative square root of 3 over 2 plus the square root of 2. What is the sine of negative 5 pi over 6? Well, sine is an odd function, so I can change this negative 5 pi over 6 to a plus if I bring a negative out to the front. So maybe I'll put a negative here. And the sine of 5 pi over 6 is 1/2. So times 1/2. So it looks like when I multiply this out, I get negative square root of 6 over 2 minus square root of 2 over 2. And those are my two roots. The last step would be to check. Now, how would I check? The way that I would check would be to take each one of these and multiply them by themselves. Multiply them by themselves. And I'm a little bit out of room, but I do think maybe I want to show this to you. So I'm going to get rid of some of what I've written here on the right, and I want to show that to you. So bear with me. Let me do some erasing. And I'm not going to show you both of them because I don't think you need to see it twice, but I do want to show it to you at least once. So let me show you the check on this. So here's how I would check it. I would check to see that the square root of 6 over 2 plus square root of 2 over 2i, if I raise that to the second power, it should equal, I'm asking does it? It should equal 1 plus the square root of 3i, right? That's just like, if I take the square root of 4 and I think that it's 2, then 2 to the second power better equal the 4. That's the same exact idea here. All right, but of course multiplying 2 by itself is a little bit easier than multiplying square root of 6 over 2 plus square root of 2 over 2i by itself. So I'm going to see if I can squeeze this in. So this is going to be square root of 6 over 2 plus square root of 2 over 2i times itself. So I'm going to have to FOIL. over 2i by itself. And I'm wondering, does it equal? Okay, so I'm going to FOIL. Square root of 6 over 2 times itself is going to get me 6. Square root of 6 times square root of 6 is 6. 2 times 2 is 4. Now I'm going to do the end terms. So plus, I'm going to get square root of 12 over 4i. Now I'm going to do the inner terms. So plus square root of 12 over 4i. And now I'm going to do the last terms, and I'm going to get plus, let's see, square root of 2 times square root of 2 is 2 over 4, and then I times I, which is I squared. All right, so hopefully I've got some things that are going to reduce here. 6 over 4 is going to reduce to 3/2. And let's see, square root of 12 over 4i plus square root of 12 over 4i is just 2 square root of 12 over 4i's plus 2/4 is 1/2, and I squared is -1. So this is going to be -1/2. Did you get that? 2 over 4 is 1/2, and I squared is -1. So that's -1/2. Okay. So let's see. I've got some like terms here. 3/2 plus -1/2 is going to give me 2/2, which is 1. That's good. I like that. Plus, what's happening with that 2 times the square root of 12 over 4i? Well, the square root of 12 is the square root of 4 times 3, and I can take the square root of 4 and call it 2. So this becomes 2 times, let me do this instead actually. Let me reduce this 2 and this 4. How about that? And then the square root of 12 turns into 2 times the square root of 3 over 2, right? And now those 2's cancel, and I'm left with 1 plus the square root of 3 times I, which sure enough equals what I started with. Boom. The check is not something that you have to do, but if you have the time to do it and you want to just test yourself and see if you can do it, I would really suggest that you go through that process. All right, so let's take a look at another example. In this example, we're being asked to find a cube root of the complex number z equal to -4 times the square root of 2 minus 4 times the square root of 2i. Before we take a look at this one though, I was watching the video from the last example, here it is, and I noticed that I forgot something when my theta was equal to -5 pi over 3. And maybe you noticed it, but toward the end, I was writing out the rectangular form of that square root, and I think I accidentally dropped the I that should have gone on that second term. So if you didn't catch that mistake that I made, go ahead and fix it now so that you don't make the same mistake that I did. All right, so let me erase that, and we will move on to doing the one that we've been asked to do. Okay, so how do we do this? We are given a complex number and it is in rectangular form. We know that the first step is to rewrite this in polar form using Euler's formula. So I'm going to say that z to the 1/3 is equal to, I'll just go ahead and write down the complex number in rectangular form, knowing that I need to change it to polar form. So my x value is equal to -4 times the square root of 2. My y value is -4 times the square root of 2. That's going to give me the ordered pair where they are the same, and that puts me in quadrant 1, 2, and 3, right? I want to remember that as I go through, because that's going to affect my theta. All right, so now I want to find r. So I'm going to take -4 times the square root of 2, and I'm going to square it, and then I'm going to do it again, and that's r squared. Now what is -4 times the square root of 2 times itself? Well, it's -4 times 4, which is 16, and and square root of 2 times square root of 2, which is 2. All right, so I get that twice. So I get 32 plus 32. Looks like 64, and the square root of 64 is 8, so that turned out nice. Now I need to find out what theta is, and I can use tangent, sine, or cosine. I'm going to use tangent because my y value and my x value are the same. And I know when that happens that I am at a multiple of pi over 4. Now, if I put this into my calculator, the calculator is going to tell me pi over 4. And that's a great answer, except that doesn't match the quadrant that I need it to be in. So in order for it to be in the quadrant I want it to be in, I have to either add pi or maybe I take away pi. Either one of those would be true. Let's just see here. So if I add pi to that, I'm going to be at 5 pi over 4. If I take away pi, I'm going to be at negative 3 pi over 4. I can use either one of these because it simply says to find a cube root. I'm only being asked to find one of them. Now, the one that I'm going to choose to use, even though it doesn't tell me to do that, on the last slide, we said that the principal square root comes from picking a theta that is between negative pi and positive pi. They didn't ask me to find the principal root on this one, but let's go ahead and just pretend like they did, and let's use that. 5 pi over 4 would be too big, right? Because pi is 4 pi over 4. Negative 3 pi over 4 would be within that interval. So I'm going to use it, even though I don't have to. It is going to be a root, and so I'm going to use it because if you're using your calculator to check these, there is a way to type this into your calculator and have it give you a complex number as a result. I want you to be able to see that answer. So, all right, so this is going to equal my r value of 8 times e to the negative 3 pi over 4 I power, and I'm going to raise that to the 1/3 power. Okay, so now I'm going to distribute that 1/3. I'm going to get 8 to the 1/3. I'm going to get e to the, let's see, negative 3 pi over 4 times 1/3. The 3's are going to cancel out. I'm left with negative pi over 4i. So that's not too bad. 8 to the 1/3 is 2. That's real nice. E to the negative pi over 4i. And that's it, right? That is the cubed root written in polar form using Euler's formula. Now, I put a check mark there, but we know I'm going to keep going because the original problem was given to me in rectangular form. I want it to end in rectangular form. So I'm going to write 2 times the cosine of negative pi over 4 plus, I'm going to remember that I this time, I times the sine of negative pi over 4. All right, and so let's see, cosine of negative pi over 4, what is that? Cosine of negative pi over 4 is square root of 2 over 2 plus, that's distributing it, so I'm going to distribute here as well. So I times 2 times the sine of negative pi over 4, which is negative root 2 over 2. And simplifying all of this, I end up with the square root of 2 minus the square root of 2i. And try that in your calculator. See if you get the same thing that I got here. I do want to point out that there are times that, like for example, if I had used 5 pi over 4, let's just imagine, let me put a red line here. If I had used 8 times e to the 5 pi over 4 I and raised that to the 1/3 power, that would have given me 8 to the 1/3 and e raised to the 5 pi over 12 I power. When I go to find out what that is in rectangular form, I no longer have an angle that I have memorized, right? 5 pi over 12 is not something that I have memorized. And so I would have to use my calculator, and I would expect a decimal approximation. So in other words, these two terms would not necessarily have nice numbers that I'm familiar with. All right, so keep that in mind. And finally, if you want to see more examples of these types of problems, there is a supplement that goes with this video, and the link is down below.